For lesson 7, we get into this idea of using inductive reasoning to be able to come up with the next idea to make a prediction. Essentially what we're looking at is patterns. You know what happened in the prior steps that'll lead us up to the next one. So the process of reasoning that a rule or a statement is true because of specific cases are true, that is our definition of inductive reasoning. So certain events have taken place that cause us to come to the idea that, hey, this is definitely going to happen. We use it all the time. Statement that is believed to be true, that is called a conjecture. They have been talking about this storm coming for quite some time now, so to believe that we are definitely getting moisture tonight, I would consider that to be a conjecture. I think we would all agree that it's probably going to happen. Statement that is believed to be true. Maybe necessarily hasn't been proven true, but we have enough evidence to say, yeah, this is going to happen. So example number 1, here's an example of our step-by-step process that we have here. We want to look at the progression of the pattern and formulate a conjecture regarding to the number of blocks that there will be in the 5th arrangement of this series. On your own, between you and your partner, or between you and the people in your row, go ahead and determine how many blocks there will be. Check with the people within your row, then we'll share it together. Allie and Liz, 15. Colby and Taslin, 15. Any others? A couple of different ways you could go about it. You can actually draw the blocks in if you want to for the 4th and 5th step. I maybe wouldn't do that. Maybe instead I would actually list the number of blocks that I'm seeing in each one. Here there's 1 block. Here's there 3. How many do I have in the next one?
6.
6. What's going to be in the 4th one? What's that? 4 more to get us to 10. So 4 is 10. So notice here we add 2, add 3, add 4. So the pattern that we're looking at here is for each step that we go, we're going to add an additional block onto what the previous number was. So to get from 10 to the next one, we would have to add 5. Most certainly, right? 15. When we look at patterns and we look at sequences and we look at the steps that we've taken to get to a point, sometimes there's that one specific case that breaks that string, and that's called a counterexample. It is an example that proves that our conjecture or statement that we came up with is no longer true, but indeed is false. It only takes one for a counterexample. You could have, 5, 6, or 7 things go right in your sequence, but as soon as you have that one step that threw it off, it no longer works. That's your counterexample. So number 2 is a good example of this. Michelle made the conjecture that the expressions 6n plus 1 and 6n minus 1 will always result in two prime numbers. This is the idea she came up with, regardless of what you plug in for n. We want to show that this conjecture is true for 1, 2, and 3, but it's not going to work for when we plug 4 in. So let's just try it. 6n plus 1, if I plug 1 in, what do I get? 7. Is that prime? Yes. 6n minus 1 would get us what? 5. That is a prime number, so that's true for 1. We could try it for 2, that would work. We could try it for 3, but let's go ahead and skip to 4. 24 plus 1 gets us 25. Is 25 prime? No, it is not. So we hit a pretty good string of it. You know, it worked for 1, 2, and 3. If we did the work, we would have seen that. But now when we try 4 and for n, it no longer works. It has busted. Okay. Questions on that?